Calculating the jumper wire size for the secondary side. Yes, using 2 runs of 300 kcmil wire rated for 320 amps each for each phase will provide the necessary current capacity of 640 amps. Powering 3 panels is acceptable to power 3 200 amps panels from the transformer in the manner described, assuming the transformer has sufficient capacity, which in this case it does at 225 kilovolt amps, and the wiring is appropriately sized. It is not legal to mount a breaker on the side of the transformer. Circuit breakers must be mounted in a separate enclosure or panel board. To calculate the primary side breaker size, consider the transformer's full load current and the inrush current. The inrush current is a momentary surge of current that occurs when the transformer is energized. The transformer full load current is 270 amps, which is the primary side rating. The inrush current is typically 6 to 10 times the full load current for transformers. Assume 7 times the full load current for this calculation. Inrush current can be calculated as 6 to 10 times 270 amps, which equals 1620 to 2700 amps. The breaker size should be large enough to handle both the full load current and the inrush current. In this case, a 3000 amps breaker would be appropriate considering the highest possible inrush current of 2700 amps. Firstly, use 2 runs of 300 kcmil wire for each phase on the secondary side. Secondly, do not mount breakers on the transformer. Thirdly, install a 3000 amps breaker on the primary side. For a more in-depth explanation of transformer wiring and breaker sizing, let's delve into the technical aspects of each component and calculation. Understanding these principles is crucial for ensuring a safe and efficient electrical system. We'll start with the secondary side wiring, where we're using 2 runs of 300 kcmil copper wire per phase. According to the National Electrical Code, specifically Table 310.16, the ampacity of 300 kcmil copper wire with a 75 degrees Celsius insulation rating is 285 amps in a raceway or cable and 320 amps when in free air. Since you are using 2 conductors per phase, the combined ampacity is 640 amps, which is sufficient to handle the 625 amps secondary current. However, there's a catch: the termination temperature rating. If the terminals of the transformer or the 200 amps breakers are only rated for 60 degrees Celsius, you must use the 60 degrees Celsius column in Table 310.16, which significantly reduces the allowable ampacity. Always verify the temperature rating of the equipment terminations to ensure compliance with the NEC. Now let's move on to the legality of mounting breakers on the transformer. The NEC is very clear on this point. Section 408.3 specifies that all overcurrent devices, including circuit breakers, must be protected from physical damage and installed in an approved enclosure. Mounting a breaker directly on the transformer violates this rule because it leaves the breaker exposed to potential physical damage and doesn't provide the required enclosure. Furthermore, Section 408.36 of the NEC requires the panel boards, which house circuit breakers, be installed in a cabinet or cut-up box designed for the purpose. This ensures that the breakers are protected from environmental factors and accidental contact. Instead of mounting breakers directly on the transformer, you must install a separate panel board or enclosure adjacent to the transformer. This panel board should be properly sized to accommodate the 3 200 amps breakers and any additional breakers that may be needed in the future. Now let's discuss the primary side breaker sizing. As you correctly pointed out, you need to consider both the full load current and the inrush current. The full load current can be calculated using the formula kilovolt amps divided by the square root of 3 times volts. In this case, the transformer is 225 kilovolt amps, and the primary voltage is 480 volts, so the full load current is 225,000 divided by the square root of 3 times 480, which equals approximately 270.6 amps. The inrush current, as you mentioned, is typically 6 to 10 times the full load current. This high inrush current is caused by the sudden magnetization of the transformer core when it's energized. The exact value of the inrush current depends on several factors, including the transformer's design, the source impedance, and the point on the voltage wave at which the transformer is energized. To protect the transformer from damage caused by the inrush current, you need to select a breaker that can withstand the surge without tripping. However, you also don't want to select a breaker that's so large that it won't protect the transformer from overload or short circuit conditions. The NEC provides guidance on breaker sizing for transformers in section 450.3. For transformers with overcurrent protection on the primary side only, the breaker rating must not exceed 125% of the transformer's full load current. In your case, 125% of 270.6 amps is approximately 338.25 amps. Therefore, a 350 amps breaker would be the maximum size allowed by the NEC. However, this doesn't take into account the inrush current. To accommodate the inrush current, you may need to use a breaker with an instantaneous trip function or a time delay breaker. An instantaneous trip breaker will trip very quickly in response to a high fault current, while a time delay breaker will allow a brief overload before tripping. The choice between these two types of breakers depends on the specific characteristics of the transformer and the load it's serving. Another important factor to consider when selecting the primary side breaker is the interrupting rating. The interrupting rating is the maximum fault current that the breaker can safely interrupt. You need to ensure that the breaker's interrupting rating is greater than the available fault current at the transformer's primary terminals. The available fault current can be calculated using a fault current calculator or by consulting with a qualified electrical engineer. If the breaker's interrupting rating is less than the available fault current, the breaker could fail during a fault condition, potentially leading to a fire or explosion. Now let's talk about the secondary side wiring in more detail. As you mentioned, you're planning to jumper the tops of the three 200 amps breakers with appropriately sized wire. This is a common practice, but it's important to ensure that the jumpers are properly sized and installed. According to the NEC, the ampacity of the jumpers must be at least equal to the sum of the ampacities of the breakers they are feeding. In your case, the sum of the ampacities of the three 200 amps breakers is 600 amps. Therefore, the jumpers must have an ampacity of at least 600 amps. As we discussed earlier, 2 runs of 300 kcmil copper wire per phase will provide an ampacity of 640 amps, which is sufficient to meet this requirement. However, it's important to ensure that the jumpers are properly terminated at both the transformer's secondary terminals and the breakers. The terminations must be rated for the size and type of conductor being used, and they must be properly torqued to ensure a secure connection. Loose or corroded connections can cause overheating and voltage drop, which can lead to equipment failure. In addition to the wire size and terminations, you also need to consider the insulation rating of the jumpers. The insulation must be rated for the voltage and temperature at which the jumpers will be operating. Typically, THHN or XHHW insulation is used for this application. These types of insulation are rated for 90 degrees Celsius in dry locations and 75 degrees Celsius in wet locations. Finally, it's important to ensure that the jumpers are properly supported and protected from physical damage. The NEC requires that conductors be supported at intervals not exceeding 4.5 feet for horizontal runs and 7.5 feet for vertical runs. The jumpers should also be protected from abrasion, impact, and other forms of physical damage. This can be accomplished by using conduit, cable trays, or other approved methods. So, to summarize, when wiring a 225 kilovolt amps transformer to power 3 200 amps panels, it's essential to follow all applicable codes and standards. This includes properly sizing the conductors, selecting appropriate overcurrent protection, and ensuring that all equipment is installed in a safe and workmanlike manner. By following these guidelines, you can create a reliable and efficient electrical system that will provide years of trouble-free service. Remember to consult with a qualified electrical engineer or inspector to ensure that your installation complies with all local and national codes. They can provide valuable guidance and help you avoid costly mistakes. Also, consider the harmonic content that nonlinear loads can inject back into the electrical system. While not directly related to the wiring and breaker sizing, harmonics can cause overheating of the transformer and conductors, leading to premature failure. If the panels will be serving a significant amount of nonlinear loads, such as variable frequency drives or electronic ballasts, it may be necessary to install a harmonic filter or use a K-rated transformer. A K-rated transformer is designed to withstand the heating effects of harmonic currents. The K rating indicates the transformer's ability to handle nonlinear loads without overheating. The higher the K rating, the greater the transformer's ability to handle harmonic currents. In addition to harmonics, voltage imbalance can also be a problem in three-phase systems. Voltage imbalance occurs when the voltages in the three phases are not equal. This can be caused by unbalanced loads or by problems with the power supply. Voltage imbalance can cause overheating of motors and other three-phase equipment, leading to premature failure. To minimize voltage imbalance, it's important to distribute the loads evenly across the three phases. This can be accomplished by carefully planning the panel board layouts and by using a phase rotation meter to verify that the loads are balanced. Also, consider the grounding system. A properly designed grounding system is essential for safety and for minimizing electrical noise. The grounding system should be designed in accordance with the NEC and should include a grounding electrode system, a grounding conductor, and equipment grounding conductors. The grounding electrode system should consist of one or more grounding electrodes, such as ground rods, ground plates, or underground metal water pipes. The grounding conductor should connect the grounding electrode system to the service equipment. The equipment grounding conductor should connect the non-current carrying metal parts of electrical equipment to the grounding system. Finally, remember to properly label all of the equipment. The transformer, panel boards, and breakers should be clearly labeled with their voltage, current, and interrupting ratings. This will help to ensure that the equipment is properly maintained and that it's not overloaded. In addition to the electrical considerations, it's also important to consider the environmental conditions. The transformer and panel board should be installed in a location that is protected from moisture, dust, and extreme temperatures. If the equipment is installed in a damp or dusty environment, it may be necessary to use enclosures that are rated for those conditions. If the equipment is installed in an area with extreme temperatures, it may be necessary to provide additional ventilation or cooling. Following these guidelines, consulting with qualified professionals, and paying attention to detail are crucial for a successful transformer installation. This will not only ensure the safety of the electrical system, but also its long-term reliability and efficiency. By taking the time to do it right, you can avoid costly problems and ensure that your electrical system meets your needs for years to come. Remember to prioritize safety and always follow the applicable codes and standards.